Today, Daniel Leitner from DLR is giving us a talk on affordance-based cognitive robotic manipulation for space and society. Sounds interesting and exciting, and I'm really looking forward what he will tell us. I know there's a video in the beginning, and I hope it's not too loud. But anyway, Daniel Leitner is a PI of the EAST project, and he has his promotion dissertation. His dissertation was here in Bremen, actually. So in 2017.
Yes.
Right? Yes.
Exactly.
Okay. So in 2017. It's a long time ago, but
still happy to be here all the time.
Yes. Okay. So now please start because of the time.
All right. Yes, exactly. Thank you very much for the introduction, and I'm honored to be here and giving a keynote. The keynote was turned from a lecture into this keynote. So in the beginning, bear with me, I will be having a bit of theory. It will be really informative. There's going to be many words on the slides. I will share them with you anyway afterwards as well for your post-reading. But then at the center of the talk, it will rocket start into something like a keynote with many videos, and it will be really interesting and exciting. But I will start with a video as well, and we'll start with a really old video of Shaky. So that's actually my favorite robotics video. It's really old. Look at it, it's like 50 years. And this robot, Shaky, it actually exhibits the same strategies that our robots today do. It's a cognitive robot. It's the first cognitive robot ever around. And it was able to perceive its environment. It was able to plan actions. It was able
These lights come on whenever Shaky intends to push an object or back away from one.
To interact with humans through text input. It would give output as well in text, in printed text output. It's really cool. It had a map of the environment. It even reacted to failure.
Shaky knows he has to maneuver box 1 around the wedge.
And even though the mechanics was not yet that sophisticated, I would say, it was able to do quite some manipulation tasks. Now, 50 years later, the robots look different, but the software architectures are almost identical from a concept point of view. What we are looking today in robotics they are called cognitive architectures. And cognitive architectures are required for cognitive robotic manipulation because it's about the understanding of how a robot interacts with the world, identifying what the issue is, what the problem is, what the task is at hand, and the robot would then try to solve that using its information sources that it has, feedback, and also predictions. Right, so cognitive robotic manipulation. So what are the core cognitive abilities? And maybe I'm repeating a few things here today as basically on the last day, but nevertheless, I would like to tell you once more. So the core cognitive abilities are considered perception, attention, action selection, memory, learning, reasoning, and metacognition. And I would just really quickly go through them with you, one by one, and give some examples of what they look like in robotics nowadays. So perception is about transferring raw input into information. So humans and animals, as well as artificial agents, do that. They have different kind of inputs that they use. So let's say humans don't have lasers, but humans have their eyes, and they're way better than any camera that we have today. So we can compensate for that. And maybe artificial agents just also receive information by data. And thus also the representations they create look kind of different. And what I have here for you is a map of a COVID-19 laboratory at the Deutsche Krebsforschungszentrum in Heidelberg. This is what human outputs of his understanding, of their understanding of what a lab looks like. They have different layers, they have maps, they have understanding where the devices are. A robot actually creates a map like that. And the question is now, how do you map them together? How do you integrate them such that a robot and a human can interact together in such a laboratory? Maybe even a human has something like that internally. Obviously, we don't know for sure, but probably to avoid collisions is something is essential. You can close your eyes and walk around for quite some time until you get into contact with something. Right. Then we do have attention. So attention is about selecting relevant information and omitting irrelevant information. So there are different concepts for that. There is selection, so choosing one from many. There is restriction, choosing only some from many. And then there's suppression, so trying to avoid the information that you don't want to have. So the picture that I show you on the right-hand side is about how a robot is trying to condense the information for a human user. So the robot knows about the environment it is in, and it knows about the task it is about to solve, and it gives the human only the information that is required to solve that task. So thinking about cleaning, the robot would not share information about how to repair something. If the robot's task is to repair it, it would probably not share the part of the cleaning. Now, the next one is about the action selection. It's about what to do next. And so the attention selection, or the attention is basically filtering that, and then the action selection is what comes after. And how does it happen? How should it happen? So this is quite an old topic, planning considered. This is like a really old architecture. It's like the T3 architecture. So this is 3 levels of how usually robots would plan in the beginning. Still, actually today, it's actually a good idea to separate your planning architectures maybe in high-level plans and low-level plans, and filter everything and synchronize everything in a word representation. This is what was done already in 96, so quite old. Now, there's a difference between planning and reaction. So planning is oftentimes only about thinking about what is the next step or the next steps, how are the next steps performed. And reaction is then if you receive feedback, if the robot is interacting with the environment, how can it change the plan? How can it circumvent maybe undesired outcomes? And then there's something like new or different approaches like dynamic action selection, including finite state machines. Behavior trees are quite popular as well these days. Then we do have the memory. Memory is really important, especially here in Bremen. We know that memory is one of the major aspects of cognition. There's differences in short-term memory, like sensory input memory. Then there is working memory. And then there's the long-term memory, which is about episodic memory, semantic memory, procedural memory, and global memory. Sometimes refer to global memory, everything that is just put aside like a heap. And a good paper that I would like you to maybe look into is this one by Tamim, our friend at KIT. He's presented recently a new architecture for this ARMA-X framework, where they try to actually implement a memory architecture as it is proposed in the literature. And now, the memory is quite important in the cognitive architecture because it's connecting all the other elements. If you want to plan, you need to know what the current state is. If you want to learn, you need to know what you have previously known and what can be what you want to achieve in the past. And so therefore, things like episodic memory and semantic memory are also key in the EASE framework. Like the narrative enables episodic memories. They try to combine a sequence of a robot's actions with semantics, and so make them more usable, reusable for further action, for further refinement. Then learning, obviously, I already said, is also important. There is declarative learning, which is basically you learn facts about the world by just trying things out. For example, if I just lift the glass and I feel that it's heavy, it's probably because it's filled. And then there is non-declarative learning, which is about learning skills. And learning skills, I mean, this is like a hot topic in robotics right now. I don't want to go into details. Recent advancement in deep learning allow us to do things like that. So having a robot turning a cube upside down in the hand, it's almost impossible to program it in a way that it is reliable because just the mechanics of the robot is so complex that every slight movement that you try to program by hand will result in something that you can almost not predict as a human because you are not in the robot. This is not your own embodiment. And so what your system is actually learning here is not how to turn the cube, but it's learning how to use its own hand in a perfect manner. So that's, as you can see, just in programmed, so the code is programmed by some of our colleagues at DLR. And then reasoning, the second to last ability, is about the processing of knowledge in general. And there's these classical reasoning methods that you would know probably, deduction, induction, and abduction. And there are some really interesting applications, so prospection, so it's predicting the future, the inference or estimation of the past, and then also measurements for action selection. And here an interesting aspect is basically reasoning about how to crack an egg. So this was done by Lars Kunze here, also did his PhD here, actually back then at TUM with Michael. And the idea was, or the question was, how can we infer how to break an egg? It's a really complex task, right? Even for a human, how do you do that? How do you parameterize your actions such that the egg actually breaks deliberately? And such that you can use the outcome later for cooking, for example. Now, the last one is about metacognition. It's about thinking about thinking. So thinking about all the other aspects in the past that I showed you. How can a robot or how can a human, an agent in general, be informed about its own understanding? So there's a part about the awareness of cognition. So being aware about your own thoughts. And then there's the second part, the regulation of your own cognition, which is about planning your own thoughts for also, and then all the other aspects that I told you about earlier, they apply now here. So for example, I can restrict my current thinking about this situation. I can try to not think about my way home because maybe this is actually making me nervous because I know that my train connection is really short. And so I would rather focus on this time right now here. So this is all about metacognition. So and then you can also monitor yourself. So sometimes you detect yourself thinking about yourself thinking. That's when monitoring happens. And there's a really cool architecture, obviously, here in Bremen that exhibits these effects. It's the NoRob architecture with the metacognitive segments here. All right, now these are the core cognitive abilities, and then there are some theories or cognitive psychology that try to leverage these abilities. And just to name you a few, there is affordances, which we'll dive into today. There's the cognitive control loop theory, and recently and quite popular these days, there is the dual process theory, and some of them are better in different things. Today, as I am talking about manipulation, we will talk about the affordances and how we use them to select actions, and how we use them also as a part of our memory architecture at DLR. All right, so what are affordances? I was discussing in the morning with Errol, it's like difficult to answer, but there's different approaches, and just to give you a glimpse, is an affordance is something that gives you a notion about how do or what to do with an object, and maybe even how to do it. That glass, for example, it affords me the information that I can drink from it. Cheers. So the initial description or representation of affordance was given by J.J. Gibson actually, it's here, already in 79. So almost as old as the first video that we saw, people were already thinking about how do humans interact with the environment. And they said that An affordance is what it offers here, the animal or the human or the agent in general. And it's interesting because that noun affordance, this verb to afford, is found, but the noun affordance was not. So Gibson made it up. So he created a new word because he wanted to describe something that he would not be able to do with the words he had in his vocabulary. Interesting enough, his student later on said, well, this is interesting, affordances, but he disagreed with his mentor in saying that it's about the perspective of the object, but that the user, like the animal or the human, has a notion in it. So that they say, well, it's about how do you perceive it? Because different entities perceive things differently. Maybe a stuffed toy for a dog is something to play, but for a human it's something that even involves emotions and things like that. Maybe it's something that you also just want to have as a decoration part. Maybe the robot would now need to think about it in an even different way. So interesting enough, this kind of affordance is now widely used in design. So that's kind of weird. You recently had a student and she was like talking to me like an affordance. It's like, how do you know about affordance? Yeah, no, it's a general thing that design students learn in their studies because of, think about digital affordances as well. Tabs in your browser. I don't know if you have had used a browser without tabs, but it's so natural nowadays that you have these tabs because they come from these paper sheets folders. It was something that they just transferred to the digital world, and it turns out that's a really good idea because like submenus, as we had them in the past, are horrible and not good to use, and so therefore design now leverages affordances as well. And most recently, I think, or most recently from my point of view is an interesting fact, Davis refined one more time that now that we know about affordances much better, it should be clarified how objects afford, for whom and under what circumstances, and I'm just giving you a picture. So all of these elements over here, they afford a similar activity, open or grasping maybe, but they look completely different. And now the question is, how can we integrate the how into the what? How can we integrate an affordance, or how can we represent affordance, the what, the how part and the what part of an affordance altogether? Now, how can we bring all of that into robotics? It's pretty abstract, right? And similar are the architectures. They're also quite abstract, I have to say. But there are three major differences. The first one being you have absolutely no idea about the environment and you want to learn something about the environment. So there's like affordance learning. Then maybe you have some notion about the environment and you have some information about the affordance and you want to integrate that. Like the pieces that you already know with the pieces that you would like to learn about the environment, or the last one, which is that you have full a priori information, and using this full a priori information, the robot would plan all the actions in a closed world assumption. Yes, something like that. All right. Just really quickly, how would you use such a system in a robot? So if you have no a priori information, then it's all about getting the information that you require. So you use maybe a vision algorithm to get a salient information about the environment, extract it, and use some heuristics, like if you have a handle-shaped object, maybe you should grasp things on a handle. If they are cone-shaped, maybe they are bottles. If they are cylinder-shaped, maybe they are containers to drink, and so on and so forth. Maybe boxes are tables, and so you can make some heuristics and try just to learn what your environment is about. The robot also does not know what action triggers what effect. It's kind of funny to see what that looks like. We will have just a picture over there in a few seconds. And planning is almost impossible because you don't know what, as I said, which action actually results in which effect. The feedback is mandatory. Without feedback, nothing will work here. And you can learn these affordances. Obviously, you can learn them in simulation, but be aware that the simulation gap applies. Okay, what about partial a priori information? That means maybe you know features, about an affordance. You know what a handle is and what to do with it. And so therefore you can detect already handles, and then you can grasp and interact with everything that has a handle. So this is like that. The features are known, and still you require a scene segmentation algorithm to identify these features, and if you identify them, the robot can try to combine information. Let's say, oh, well, there's a cylindrical and a handle affordance, so maybe this is a mug. So, and somehow the system would create or learn new facts about the environment just also by doing that. Like if you grasp the handle and the cylinder next to it moves with it, probably that is a mug. And so you can learn object affordances from feature-based affordances. And actually what is the most easy way to deal with affordances is actually informing the robot about them, which is reasonable because we know them, right? So you probably don't need to learn what you already know. If you know what a mug is, what a mug looks like, there's dozens of pictures, millions of pictures of mugs in the internet. You can learn them. You can recognize mugs if you know what the mug is, because the algorithm tells you, then you know that you can grasp it on the handle, and it's pretty straightforward. So maybe even better, you have a cat model right away, and so you perfectly know how to grasp it even. So the relation is known in advance. We know the object, we know the affordance. They can be recognized. We even know the models maybe. We know them perfectly. And we have this, what I already informed you about, the working memory. So we realize a concentrated working memory, and all the information is stored in there. And as the information is collected, the robot can just tell you, well, this is a mug, and can grasp it, and there's a bottle, I can use it, and then I can pour into it. You can still use feedback to update the information, but most of the time it's probably not required for the poor information about the affordance. If you wanted the interaction part, it's probably an interesting part to learn this as well. All right, so what can we do with affordances in robotics? So the three examples that I gave you, if you have no information, it's pretty difficult. So there's this paper where the authors try to learn an affordance. So what is the best tool to rake this ball into this black area? Pretty interesting task. And you would see that probably and that's interesting because now you see what an affordance is like. So maybe what's the best tool to get the ball into the black area? Light blue? Light blue is good, I think. Maybe the orange one. The green one is pretty bad. Light blue is also, like the dark blue is also okay-ish, but I think just this additional hook gives you something that just helps a bit more. Now, is that an affordance? That's really difficult, right? What is the affordance called? Rakeable? I don't know. Anyways, then there's if you have partial information, you can use this to operate robots via affordances. There's something called the affordance templates, so they gave it a creative name. And with these affordance templates, the authors actually controlled their robot here. This is the Valkyrie robot of NASA in the DARPA challenge. And it's a pretty cool concept because you can say, well, I have something that is turnable, I have something that is liftable, and you just overlay it into your environment and a control algorithm, and then the user can manipulate that virtual affordance, and the robot would know what this means with respect to his manipulators, with respect to his end effectors, and thus do exactly that motion that you want to control it from afar. And then there's the full priori information, and this can be used for planning because you know all the preconditions of an action, you know all the effects of an action, you know all the objects that relate to an object. And this is something that I was essentially, this is my first publication down here, and I'll tell you something about it at the very end of the presentation. But the thing is, so we call this action templates, and using the full information, it's pretty practical to control our robots in different environments, and we will go now into details about that. So this is now where let's say the interesting part starts, right? So now we have the fundamentals for everybody. I think we know what the cognitive abilities are. We know why affordances try to, at least from my point of view, how we can use them in planning. And this is how I implemented it back then. The action templates, they consist of two parts, a symbolic representation and a geometric representation. And the symbolic representation describes the what of the affordance. So what are we talking about in planning domain definition language, PDDL, still used as a standard in the planning competitions that you can see, for example, at these planning conferences. And the second part is the geometric representation, which is about the how. And the how part is here again divided in information that the robot receives from the object database that it has, from the knowledge information, like from its memory. And then we have a sequence of actions that the robot is then interpreting again. So the idea is that these action templates would be robot agnostic. And you can see them here. So there's some plan to frame. Oh, that's reasonable that things like that happen. All right, let me just do that. And now the where was I? Yeah, this is generic, and the robot has an interpreter for these actions and then tries to solve them. For example, the planning of a motion for a humanoid robot would involve the whole body. You can give this information to a drone, and it would just try to do the manipulation part, maybe attached, having a wiper with the full body. Okay, and then planning with action templates is a hybrid process, because I told you it's two parts anyways. So we are looking into how can a robot solve that from a symbolic point of view. Cleaning here, for example. How can the robot clean with this brush the breadcrumbs from such a breadboard? Like from a symbolic point of view, it's pretty straightforward. It's only about picking this brush and then brushing. But as you can see, if the robot tries to do that, actually it will not be able, because the bristles are upside down, and the robot will fail. Now, so that means it will involve a bit more. And obviously the robot could try with the right hand or with the left hand. It doesn't make a difference. So the robot needs to come up with a different symbolic alternative. So it would probably schedule a handover action, taking the brush with one hand and trying to hand it over. And here as well, in the handover process, there may be geometric alternatives. So also geometrically, we have to search for alternatives, maybe even to backtrack. And this is a configuration that works out. So in the middle, it's pretty good. The robot can hand over the tool and then start the cleaning process in the correct orientation. Now, the robot also needs to somehow be able to parameterize an action with respect to the actual outcome. So we want to have an outcome that is fitting to the task. In the cleaning, for example, we want to have different tasks solved. Maybe we want to just wipe away some medium. Maybe we want to collect a medium. Maybe we want to just, also, what do we have here? Scrubbing means that you just want to try to use a medium in order to give some action to some crustacean maybe in your coffee mug. And the question is, how can a robot be parameterized? And here I was working together with a colleague of mine, Alex Dietrich, DLR. He is a control specialist, and we tried to make an informed controller, essentially. So they have a really good whole body controller. And the question was, how can we use this knowledge-based method to parameterize the planner in an optimal way? And as you can see here, we give the robot information about stiffnesses and forces, and with this the robot is able then to actually clean these tasks. And then feedback is important as a last step. If you have this robot parameterized with your action that is defined based on an affordance from your object, you also want to know if the outcome is correct. And in this case here, I implemented a kind of simple model. Maybe in ease it would be called a pragmatic everyday activity manifold, so a PEM. It's like a shortcut to an information processing idea. So in this case, it's just basically particles that somehow represent what the cleaning task looks like. It's kind of vague. It does not reflect 100% what the environment looks like, but it's a good match. So you can see here the internal representation of the robot matches quite well, and the robot can even use the information about forces and the desired positions and identify if the action was executed correctly or not. And then if you go even one step further, the robot may even be able to learn from that. Here we back then put the information into ease, into OpenEase, and you could query this database, this information for things like, oh, please tell me, where did the robot feel a force, but not exert a cleaning action? And you can see here, this was the time when the robot was pushed, and probably you could learn from that some human interaction was here maybe wanted or not wanted. Yeah, well, that's something that you could then see about. How do we bring that into space? So now this is where the thing starts to become a keynote for sure. So we go into space. The idea is actually back then when we were developing these affordances, they were, I had in mind that they were pretty practical for everyday activities. But then ESA came around and they asked us, hey, can we somehow control a robot from the space station to do our, let's say, dirty work on ground? I was like, yeah, well, dirty work, that's about what I'm doing anyways, so let's have a look. So still today, the state of the art in space robotics is quite different from what we know in at least here in academia, because most of the time these robots are teleoperated. This is a picture of the control room of the Curiosity or Perseverance rover at JPL, sorry. And they control robots with activity plans. So it's like a schedule where they exactly know at which time in the day of Mars a robot will do which action for how long. And when I say action, they are pretty primitive. Usually they are like, say, essentially drive forward 0.5 meters, turn around by 20 degrees, move again forward, move the arm to a certain position, make a photo, move to another position, make another photo. So it's pretty boring, essentially, but it's really detailed. And they have feedback on 2D screens, some are even 3D screens, and they create maps of hazards, and then they use this information for further planning. So this is actually the things you see. Here's this activity plan, here's the 2D information, this is a close-up picture of the wheel. That's Perseverance, considering the wheel, this is Perseverance, so the latest rover. And then they have these hazard maps maybe over here, and then, yeah, create a new schedule, send it up, and then they know what the robot would do again. Autonomy is coming, though. So there are some actions that require the robot to do planning. This picture here is actually a prime example. You wouldn't know, but this motion to create this selfie, they are created from a motion planner, because the robot's camera is not able to collect all the information about the system on one shot, so it makes a sequence, and as the robot moves the arm, it has to plan the motion of the arm, checking for inverse kinematics, and funny enough, this is not the first picture they took. The first picture, they could only make it halfway through, and the robot failed because it had an inverse kinematic error, and then the system just crashed. So, so basically, the planner stopped, and when they came back the other day, they got half a picture, and the system reported inverse kinematic reachability failure. So that's kind of funny, and you can see how far the autonomy is currently at the Mars, right? So not that big. But the driving, on the other hand, is now much better, so they can now detect hazards on the fly. You just give the robot a goal that is, let's say, 500 meters in that direction, and it's like, try to go as fast as possible, as far as possible, and then the system, I think the current record was 245 meters autonomously, and the system then had to stop because there was maybe a big rock in the way, and it had to stop. So there's autonomy is there, but only up to a certain level where the engineers really trust the autonomy. The feedback is difficult because of the high time delays. So considering Mars, it's 45 minutes in the worst case. That means you send a signal to the planet, the robot does something, and 45 minutes later you receive the information, maybe as a video feed, maybe as a picture. And so this is really, really cumbersome to control a robot like that. Now the next steps in crewed exploration of Moon and Mars are thus different. So we think that it is actually crucial that you send the astronauts with them. But they would not be on the planet, but they would be orbiting the planet. So the idea is You have the astronauts in the orbit controlling the robot on ground to have lower time delay and more frequent interaction with the system. There are different methods that you could apply. Direct control, like with a force feedback joystick. Supervised autonomy, which means you have a high-level command. And then a mixture of both. And I will go through all of them with you now. So this is the first way. It's the direct teleoperation. You can see here Luca Parmitano. It's an Italian astronaut controlling a rover at ESA in 2019 from the space station with something called a Sigma device, which is usually used in minimal invasive surgery. Here you can see it, directly controlling the robot in a high time delay. This was about a second. So this is what it looks like from the user's perspective, and this was the task collecting a rock. It's a pretty good task for direct control because we maybe don't know the rock. And maybe we want to grasp it in a very, very delicate way. So therefore, this is a good scenario here. Now, it's cognitively quite difficult because even though maybe the time delays are low, when they start to get over 1 second, it's still difficult because like you're moving your joystick, nothing happens, but then you see something happening and then you stop it, but for another second the robot moves and you're like in panic and you're going to the other direction and it's a mess, right? So it works. It's also stable. We implemented some algorithms published in Science that allow us to be to do geologic in science stable, but still difficult from a cognitive perspective for the human. So now so we thought, okay, well, why don't use the action templates? Because as they afford to the robot what the robot can do with an object, we could also forward this information about the affordance to a user on the station. So they would click on an object. You can see it here highlighted. The robot would give you then the information what you can do with the object based on the information that is given in the action template, and then just by clicking one of them and then sending it to the robot would execute that action, but maybe even a sequence of actions that lead to this goal state. And this is what it looks like on the space station. This was 2018. This is Alexander Gerst, a German astronaut, controlling Justin during his experiment on the 17th of August 2018. He was controlling Justin here. The idea was that we give the astronauts increasingly complex tasks. And here we actually faced Alex with something really, really difficult. So there was we simulated an issue with one of the modules. And even though it was never trained, Alex was pretty quick in understanding how to interact with the robot in that fashion. And you can see that the team together solved the task actually fluently. So this was what we hoped for, but we wouldn't know. And from there on, we decided to try to see if we can combine the methods because we realized that both of them are crucial. Funny enough, if you ask the astronauts, Luca Parmitano, only having the direct control, what would you like to improve? And he would be like, I would like to have more autonomy for the robot, such that the robot does more things on its own. All right, we can do that. And then if you ask Alex Gerst on the other side, what would you like to improve? He would be like, oh, I would like to have more direct control. And like, oh man, okay. Now our latest experiments are now actually focusing on trying to integrate them, and this is what we call sliding autonomy. Sliding autonomy is about trying to figure out what is the best way of controlling a robot during what time. And again, affordance play a crucial role here. So what is the best affordance for a user in that sense? And this is Samantha Cristoforetti, again, an Italian astronaut from ESA. And here you saw that the robot initially grasped this handle autonomously, but the moment that we would like to know what the handle feels like, we would rather give Sam the controls, and she can feel it with the force reflection. The issue with sliding autonomy is that the information that we created previously, creating our closed world assumption, can be destroyed because the user actually is changing this information during direct control. And during autonomous operations, because during autonomy, maybe the robot is unaware of error situation. You can see here, this is like the data interface probe, like a plug. to charge the robot maybe, or to get some information from this module. If it fails, without feedback, without proper feedback, the robot would not know that it failed. And during Terra operation, as the user changes the environment, through their interaction, the robot is unaware of the effects. So because then the reasoning system does not have any more the information about what was the planned action of the user, because it doesn't know, right? The user could try to do anything, and we even realized sometimes these astronauts try to do everything to destroy your robot. So how can we infer the state changes? This became a fundamental question that we were focusing in the past, and one of them is physics simulations. So physics simulation, a digital twin essentially, using for example, Gazebo as a source of information. Now the problem is these simulations are never accurate, so the question we wanted to answer is how can we make them more accurate? How can we maybe not even make the simulation more accurate, but how can we make the results more accurate? The results about the prediction. So we looked at the different simulations. This is work actually done in EASE. We are looking into, this is a recent publication about physics engines. So ISAC-Sim was really new back then. It was already listed. If you would do it again, I think this would increase here for sure. There's new simulations as well. But the thing is, yeah, we were not sure which one to use. Now, we came up with an idea, actually. We thought, okay, we know that the simulations are usually done with a special purpose. So there's simulation for minimal invasive surgery. There's a simulation for drones. There's a simulation for grasping. Why don't we, let's say, combine them the way they are meant to be? So for grasping, for example, we say unless a robot is grasping something, we don't focus on the grasping, but the moment that the robot grasps something, we focus on the grasp and use a simulation that is especially tailored to make a grasp simulation as accurate as possible. And this is what you can see here in the video. On the left-hand side, you have the pure physics, which you would see from Gazebo, and the first thing that you would notice is that it just immediately explodes. The robot grasps the ball and it's just somewhere. The next thing is you use physics, but you use some heuristics. This is often done, let's say, the moment that you know you want to grasp something, you just bind it, so you disable the physics. That works a bit better, but then we thought, okay, what about the moment that we know that the grasping should happen, we just switch to our grasp simulator. So in Gazebo, the object disappears, but in our second simulator, which is not visualized, we have a very, very accurate estimation of where the object is. And the moment we release it again, we know where it is, and then in the overall simulation, the outcome is much better. Now, how can we use that during supervised autonomy? During sliding autonomy is ongoing goals. So we want to find out how can we really integrate that now in the system, because obviously runtimes play a crucial role, so we have to be real-time capable. We have to be sure that all the updates or synchronizations are done correctly, and this is essentially future work. All right. Society. There was society in the title. So how can we come down from space to ground? And actually, right after the first surface avatar experiments, we thought maybe this could be of use for somebody else, for someone else, because we figured that it was really actually intuitive. So the astronauts, some of them even without training, flying over from, I think it is the US module, came over and say, hey, what are you doing there, Paolo? And then Paolo was saying, well, you know, that's pretty cool. I can control a robot on Earth. And he taught them on the flight how to use the system. And we thought, okay, if it's that intuitive, I mean, obviously, astronauts are exceptional people, but they are generalists, right? They are not roboticists. We thought, can we use it for different purposes? And here you can see, yes, maybe we can in a scenario where we interact with humans on ground. And this is a project called Smile Together, the second iteration of the SMILE project, which is all about elderly care or care for people that are by now unable to move because maybe they have a disease or had a stroke. And it turns out that this is working really well. And So we are currently looking into also interactions with stakeholders from this healthcare sector in order to identify how we can use robots in the future, how can we develop methods, how can we actually create even new jobs for how to control robots in these areas. All right, and then one last element that I would like to present you before I stop my presentation is shared autonomy. That means that you have the autonomous part and the direct control at the same time, and the robot and the human control, let's say, a part of the human for a certain task in the same time. This was motivated by this example. This is a person with spinal muscle atrophy. So that means she is no longer able to control her muscles because the nerve system in her spinal cord degenerated. And so essentially at some point in her life, she could no longer move, and she is bound to the wheelchair. So everything head up is still movable, but everything below is no longer movable. But interesting enough is that the information that she's trying to send to her muscles is still received at the muscle, but it's not strong enough to activate the muscle. And it's also really, really of bad quality. It's like with a lot of noise. But we can detect it. So underneath these red tapes, there's EMG sensors. And with these EMG sensors, we can identify how the user would like to use their muscles, and we can identify that and transfer it to a motion for the user, like for the robot. But as you can see, it's pretty difficult, right? So she tried to do a really easy task, grasping something and drink, but already that was pretty difficult. So we thought, okay, how can we now increase the capabilities of that user by decreasing the complexity of the task? And this is what we came up with. We said, well, actually, we know what the world affords us. We know what the things are about, right? We know that if you have a glass in your hand, the only thing that you can do with it is either, reasonable thing to do, is either just put it down again or drink from it, right? So why not use this information to assist the users? So we came up with something called the shared control templates. The shared control templates are based on affordances as well. They describe a skill essentially to assist a user in a certain task. It's not about the autonomy in the first place. And so therefore, what we do is we implement for each task a finite state machine that a user can traverse through simple inputs forward and backward using a definition that includes two things: an input mapping, so how do we map this information from the user's muscles to the action, and the current constraint. So the input mapping is essentially the information that we receive is probably like maybe we just have 3 electrodes and they get the information maybe forward, backward, left, right, up, down, like positive or negative, we can distinguish. And we map these then to the most complex actions, which involve usually rotations as well, and some of them are maybe even combined. And we limit the possibilities for the user as we give them these constraints. So that means if you want to pour, yeah, it's not reasonable just like to pour like all the way upside down, and maybe it's not reasonable to go very, very high up, even though I know that Michael tries or always likes to show this movie of this barkeeper, which has like really fancy motions. For these people, it's just fine if it's like ordinary. And this is really new. It's like a video of March where we use this framework in a competition in the Cyberthlon. This is Matthias. Matthias also has spinal muscle atrophy, and he is a pilot of Eden, the wheelchair. And as he is piloting Eden with the shared control templates, he's able to move a bit more, so he has still the ability to move his hands, but as you can see, also very, very limited, just like that. It's too difficult for him to make complex motions with the hand as well. But using these shared control templates, he's able to do quite some complex tasks really quick. So you can see it here. I mean, it's like involving a lot of orientation. There's a lot of degrees of freedom moving with the robot. And then he even now he's looking at the tablets, just seeing if the robot understands what he understands, if they have the same affordance, if they share the affordance, and now they do. So he still has the head switch, so he can change now to driving mode. And the task here is to grasp these difficult objects from the shelf. As you can see it here, Matthias checks that the robot perceives the objects correctly, and there's a camera mounted on the right-hand side. And as the as the objects are perceived, he can control the robot, and the robot can grasp the actions. Actually, I would like to show you the last action, the last object, because I think this is the most impressive one. Where's my mouse? So there's 4 actions, 4 tasks that they have to grasp. Here we are. And the last one, the affordance for, oh, I spoiled it. The action for the last one even involves a complicated strategy. So the task is like, it's not just grasping it, because they know it's impossible to grasp such a small object from just on the middle of the table. So the action involves pulling the object onto the corner and then just grasping it from underneath. So you can implement that into your shared control template if you need to. All right. One more application that we implemented the shared control templates in are now minimal invasive surgery. Now it's pretty difficult to describe an affordance to a surgery, I have to say, but nevertheless, the concept still holds. Shared control templates can be used here as well. If we know about the task, if we know about the sequence that we want to interact with, if, for example, here, knowing about the orientation and the direction, we want to move a tool, here represented by a pen, maybe it's a scalpel, we can actually assist the user here. And here we tried something different, because maybe in the wheelchair, you want to increase the autonomy of the user by increasing the autonomy of the system. In a surgery, you do not want to have increased autonomy of a robot. We want to know where the surgeon actually cuts. So we do not want to have the robot cut somewhere in my body, right? So therefore, what we do is we give this information to the robot uses this information for a plan, it maybe even is executing it, but as long as the surgeon here, Katharina, has the hand on the joystick, she can always stop it or accelerate and decelerate it, or even deviate the motion. So it's a type of shared control where the control is again slightly shifted from the robot to the user, but the autonomy is still with the system and supervised by the human, right? For some tasks that are pretty difficult actually for young surgeons, for example, handing over the needle, this may be actually really, really good to use, because then the robot is not in contact with this with the patient here, but they can learn how the robot is best used, how the robot is best used, how to hand over maybe the needle. All right. Yeah, and then yet another video. I think that's the last one. Obviously, with the COVID-19 pandemic, I started with COVID. I'm ending now with COVID again. That's pretty neat. So we were also thinking about how can we use our knowledge to assist like laboratory workers in their daily work. And in this case, what we're trying to do is here that we show the robot a motion, an action, and the robot would identify what our affordance was, what was our reasoning about it. So this is the idea is that the robot has a database of all the skills in the background as well, so like an action template, maybe a shared control template. And as we move the robot and we identify what the tasks are about, the robot would identify that, okay, it's about inserting maybe the pipette tips or getting the fluids or doing the pipetting on its own. And the robot would not replicate the motion that was trained by the user, but it would only use the information about what was the goal of the user and then use the own skills of the system to replicate the task rather than the motions. So again here, different way of how we are using today the way of affordances. So now the conclusion, and actually I have to commit the conclusion. I did it right before the presentation and I did it right after I had the discussion in the morning with Errol, because we were discussing So about affordances, I will tell him, yeah, I will present about affordances. He said, yeah, you know, my first work was this one about the affordances. I was like, yeah, I know. And actually it came to me how I was becoming aware of affordances, just basically like the Holy Maria came to Jesus, like by a review. Because I've submitted my paper and I was not aware about affordances, and I just said, well, I created something that I can control a robot with, and then I got the review and I said, well, what you're actually describing are affordances. And then one of the suggestions of the papers that I should read is this one by Errol, To Afford or Not to Afford, and looking back at 10 years of affordances with robots, definitely afford. Thank you very much.